Welcome back to the continuation of some design tools, and here we're sort of talking about compaction. And one of the design tools you might find used in this area would be related to algorithms known as simulated annealing, or their variants. And it basically performs optimization by moving geometries randomly. Well, it's not totally randomly, of course, it's going to be somewhat directed, but it's certainly a very useful and a very powerful technique. And if you're going to learn any Monte Carlo type of simulation technique, I'd highly recommend it being simulated annealing. In any event, if a change improves the design with simulated annealing, the change is kept. If the change degrades the design, then the change is probabilistically kept, and that's under the control of a control parameter. So this enables the algorithm to escape local minima in its optimization, and it's basically what you'd think of it as a sort of directed luck or directed serendipity. In general, with respect to compaction, there are difficulties and some improvements. It may be somewhat dependent upon the initial layout. Simple compaction, would not be wouldn't produce a very good layout if you didn't have some intelligence associated with it. And some of that might be the insertion of some jogs or bends in the connection wires that may not be overly evident or self-evident. Or other things you may do is swap components instead of simply moving them. So that may also improve compaction. But in any event, all of this sort of basically begs for the use of heuristics. And heuristics are sort of rules of thumbs or things that can guide you to help you improve upon, in this particular case, compacting a layout. Some of the difficulties, also you have to keep in mind that sometimes you're not going to be allowed to remove spacing because it might be needed for specific reasons. Some might be design rules. Those would be process driven, for example, which would prevent you from putting two layers of different materials too close together. Others might be crosstalk driven or interference driven, where maybe perhaps you're making two long wires that are close together and you don't want them to be too close, so there's going to be crosstalk, which would basically potentially disturb a circuit signal on one line when the other is toggling. So both are types of design rules that you may have to make sure you don't violate when you're compacting something. In other cases, you might have to ensure some minimum distance to ensure reliability, and those again would probably be built into the process design rules. In any event, a place and route tool that was built by a fairly well-known professor at U of T right now, it used to be at Altera, was called VPR, and it uses a simulated annealing algorithm effectively under the hood, and that's what you're using within the Quartus tool set in all the labs that you're working on. So some of the difficulties and improvements, again, most of the designs are going to take advantage of things like hierarchical design, so you don't want the movement of one object to affect objects at different layers of the hierarchy, and you're kind of hoping that if you do DRC, that design rule checking at one layer, it's perhaps not needed at the next layer, hopefully, but of course it would probably be needed at the boundary of all the cells that you've perhaps previously DRC'd and then connected up. And compaction must not change separation, which is essential to design, and the example there would be the rail separation. So those are the power rails in standard cells, and clearly port locations, which you couldn't move around or you wouldn't be able to connect to them later. With respect to some cell generation, we're going to look at initially a very old kind of idea. It's called a sea of gates. It predates FPGAs, or it might have been called a gate array. So it's an array of transistors or gates which are connected together to produce the desired logic functions. Simple idea, but not very efficient for area usage at all. In any event, place and route type of synthesis may be used to create these types of layouts. It's similar to the place and route for logic cells. Typically all the gates have similar structures, and you could either place and route within a cell or place and route a bunch of cells, and there again you're taking advantage of something which is a design methodology or paradigm of design and conquer. For example, here is a CMOS cell generator where you might have the PFETs placed in a single row beneath the power rail, the NFETs in a single row above the ground rail, and then the area between the PFETs and NFETs are used to connect up the logic of the gates. And in some cases, those transistor gates would have already been present. In a modern FPGA, the idea would be that these lookup tables are already present, and then you're effectively connecting those up through programmable routing resources and switches. So the ideas are similar, but certainly have evolved a lot over the past 20 years. So here's a simple example of an array of transistors. This little picture up here is supposed to represent a FET. In this particular circle would be the gate contact for the FET. So certainly they're not circular. It's just drawn in this fashion to represent a schematic, not quite at a transistor level, but a little closer to layout. So here's the NFETs, the PFETs, connecting up VDD and ground, connecting up some gates, completing the wiring. And when you do this, you sort of see that you end up with, at least down here, it's obvious you've connected up 2 transistors in series. Up here, a little less obvious, 2 transistors in parallel, and we know that that's our NAND gate. So an in-class assignment, 7.2 would be to route this function f, which is equal to this function over here. So take a little bit of time, I guess, and try to route that. So it's due now and due now. I guess I'll have to hand that out in advance so that you can actually do that. It's very interesting, though, or one of the interesting things I thought I'd do after you take a kick at this is put that function f into Quartus and see what comes out. So in this particular case, certainly got the schematic, which is exactly logic function from right here. I mean, for example, there was the AB NAND, so there's the AB NAND. You pull that circle back to there, and that circle back to there would give us the NOR and the NAND, and then another NOR, and then another AND on the output, or a NAND on the output rather. I did get a warning that the output was tied to VDD or ground, and as you can sort of see here, even though it synthesized it to this, I don't know if that logic would have reduced any further, but the output's always a 1. So something to be aware of in any event. And in any event, I also was a bit surprised at that. So here's another example of a cell generator, perhaps a little closer to layout, where you sort of see a routing area, NFET area, PFET area, and then a connection up of the gates so that you end up building a particular a gate, which is an AND gate. And there might be a trade-off of some flexibility here where perhaps you don't have as much control over the widths of the transistors as you might otherwise like to have. Specific generators are used for regular structures such as registers, buffers, counters, often used to produce high-performance components with a very repetitive structure, and a unique generator may be required for each module. What would be very nice to have within these generators, of course, is some capability of scaling transistors to basically give them more drive, and that basically falls under the area of parameter optimization, which could be included in a generator. And then once these things are laid out, again, additional compaction might be performed on the layout after synthesis to reduce an even smaller layout area. Again, this is very low-level, cell generation stuff that you're not likely to encounter, but perhaps may want to be aware of. Following on as design tools, logic minimization, you're certainly well aware of those. From other courses, logic minimization techniques have been around a lot longer than IC design. Plenty of algorithms exist, for example, for finding the prime implicants of a circuit, and that means you could have no further simplification. An example is Quine-McCluskey algorithm from the 50s, and more familiar, known to you as a Carnot map. One is a tabular and one's a graphical representation of basically the same functionality. In IC design, though, there might be certain restrictions that are placed on logic minimization that could be important. For example, the Quine-McCluskey algorithm optimizes for a single output function, which may or may not be the case, and often a combinational circuit expresses a minimum number of prime implicants may not necessarily be the fastest circuit. Other things that you have to consider might be fan-out when you're accounting for speed. Similarly, minimized functions don't always lead to the smallest area of structures because there might be some constraints in it where you're basically implementing something in a logic like a 2-level structure. Minimized circuits may not also be as testable or as fault tolerant, so some redundancy might be intentionally added to increase reliability, and here's an example of adding a redundant loop in a Carnot map to remove a static hazard. So at this point in time, we'll take a brief break.